Hi everyone. So in this next episode of our MIPS video series on physical AI, I'm going to be talking to Sean Murphy, and we're going to be discussing the ACT use cases that are involved. Hi Sean, how are you?
Hey, Mike, I'm doing well. How are you?
Good to see you again. Great. So
Good to see
maybe
you.
you could start off with basically discussing where things currently are and when they need to be in the future.
Yeah, in the ACT phase, we are really, solving real-time control problems. So that's where we're actually physically interacting with the real world. And we can kind of break down that problem into really three main pieces: reading and writing from sensors, interrupting the core, and computing your control algorithm. And our main goal is to reduce that latency as much as possible. And if you kind of look at the current microcontroller CPU landscape, you'll see a mix of solutions from general purpose CPUs to proprietary CPUs and even some accelerators in there
Yeah.
as well. So it's a pretty heterogeneous application field today.
Hmm.
And it's really not optimal from a software programming perspective as well as even a performance perspective.
Because there's too many proprietary sort of things that are,
That's
it's
right.
all fragmented then basically, is
That's
that?
right. And we see a
Yeah.
lot of customer demand for more standardized solutions, but still meeting those key performance points in a standardized way.
Yeah, okay. So in that respect, then, is the move towards more open source sort of methodology going to be important because that's going to bring some sort of level of consistency throughout the whole thing?
Yeah, that's right. And this is really where I think RISC-V really shines as an architecture and
Sure.
as kind of a backbone for everything MIPS is doing moving forward. So as you know, RISC-V is an open source instruction set architecture and really gives us a strong foundation to standardize, but also gives us plenty of flexibility to innovate and give those performance KPIs that customers are looking for. And then,
Mhm.
probably most importantly, because it's growing so fast and has large ecosystem support, it's
Yeah.
easy to program on, has large compiler support from all the standard suppliers that you'd expect.
Okay. So at the moment, we're still in a little bit like the Wild West phase. There's no, it's all a bit, everyone's sort of doing something different. No one's really sort of, and obviously Risk 5 gives a way of trying to make that a bit more homogenous rather than
Yeah,
sort of
that's
being
right. And
sort of,
and
yeah.
and I think, I mean, if you look at what's shipping today, that's in vehicles today, in robotics today, yeah, it's a
Yeah.
pretty mixed bag of CPU architectures, as well as even accelerators in order to solve the problems. So yeah, definitely not standardized. Definitely a lot of room for innovation around both standardization, but also around solving the problem in a more efficient way.
But I guess that must be holding up the whole adoption as well because companies are not keen to get involved if they feel that it's going to be more complicated than it needs to be. So I guess by moving to open source, that's also going to accelerate the sort of uptake. Yeah.
Yeah, that's right. I mean, especially with an open source architecture that can scale from the low end to the high end, because
Mm,
particularly when you look at, this kind of mixed bag of solutions today, that
mm,
also makes it harder for customers scaling to even higher performance processes, because a lot of times those proprietary architectures are very focused only on the MCU space and don't
right.
necessarily scale to the high end space. And RISC-V really gives you that flexibility to grow from the very low end to the very high end and allows MIPS to build a portfolio that scales the same way. And so in that way, your software investment can be, reduced or simplified to, if I'm investing in RISC-V for this microcontroller ACT problem, I can also apply it to the sense problem. I can also apply it to the think problem. I can also
Yeah.
apply it to the communications problem. And that's how we view the physical AI problem, so that you can do more single point investment and apply to a lot of different applications and performance levels, all on RISC-V.
Which makes sense because obviously, they don't want to invest in something and then feel that's a bit of a dead end for them,
That's right.
or that there's, you're going to have different solutions for different parts of the problem.
That's
And
right.
also, I guess, is, to some extent, if you've got a solution now, you want it to scale up because you don't know what functionality you might need in a 2 years time when you've got to upgrade it to something else. And I guess, you want to have that headroom that you can add extra functionality without again having to start again from scratch, I guess, basically. Yeah.
Yeah, that's right. And let's be honest, right? The bar is high for customers to switch to a new architecture, right? So that bar being high means I have to deliver, ease of programming and performance
Yeah.
points. But like you said, if I'm gonna move things over to a new architecture, I need trust that I'm future proofing my designs for scaling up
Yeah.
or down across the portfolio range. Absolutely.
That makes sense. But then, as you say, then you've got the scalability, you've got the sort of the ability to utilize it in multiple ways. You've got the ecosystem support as well, because obviously that's really important. You don't want to be stuck with something that you've got no real backup
That's right.
so that, and I guess a lot of these companies are making those first investments in edge AI are probably quite cautious about what they're going to do with it, because they don't want to spend a lot of money and then find out that it's a dud basically. So I guess RISC-V would give them that much more reassurance, because it's so well backed by different sort of organizations, and that helps to. Okay.
Yeah, it gives some reassurance, especially because the ecosystem partners are really there at this point. I mean, maybe 10 years ago you couldn't say that, but I would argue RISC-V ecosystem is ready to go today, even on things like automotive and more niche requirement type applications. RISC-V has really grown on the ecosystem front.
Okay. So that's the good arguments, I guess, that moving to RISC-V, and that's why MIPS obviously is supporting it, and there's definitely some real benefits of that. Let's maybe deal with some of the use cases then. So obviously, sort of with some of your colleagues, we've already talked about the sense
Yep.
and the think, and now the act sort of side of it. So basically, data's coming in, that's being dealt with by the think element, by sort of the computation being done and the decisions being made at low latency about what's going to happen next, and then how does the act come into that, and how was that sort of implemented then from there?
Yeah, so I mean, I think one of the easiest examples is just to think about a robotic system, maybe on a factory floor. So if you think on the sense, think, act, communicate stack that we talk about, right? You'll have some sort of brain doing your high level motion control, choosing where pathfinding and where to actually put things.
Sure.
And then you'll have sensing at the edge where you're sensing all your input signals. And then the act portion is really at the edge of the robot itself, meaning actually actuating motors and interacting with the physical world. So when you think about it that way, the use cases we're talking about on the act side are motor control. We're also talking about digital power conversion.
Yeah.
And we're also talking about battery management. Those are kind of like the key real time control application spaces that we usually talk to customers about. And again, in those applications, your goal as a system designer is to reduce the latency of that real time control loop as much as possible. So in each of those applications, there's a control loop running that is choosing how to actually turn the motor, or how to control the current within a power conversion phase, or how to monitor a battery.
Yeah, and like you say, each of those is being concept data. So the sense data is coming in all the time. That's being
Correct.
computed, and then it's continuing to sort of reevaluate what's going on and what.
Exactly.
So maybe let's look at all three of those just in a little bit more depth. Then, so maybe we should start with the motor control one. So, maybe you could give us a little bit more detail of how that sort of pans out.
Yeah. So motor control is traditionally controlled by what's called a field-oriented control algorithm. And again, you're sensing phase current data from the motor power stage, and then you are interrupting the core, telling the core that you have new data available, and then you run that FOC algorithm on the CPU itself, and then you generate new PWM values to push out onto the system. And that is again the latency we are trying to reduce. And so by doing that, you can kind of enable some system level benefits like higher RPM motors, smaller, lighter motors, higher frequency motors, and the like, and also give more fine control for things like robotics, where you really need that fine, precise control. And so when we look at, we've talked a lot about the overall view of the market, and kind of where the CPU space is today. But specifically with motor control, we have a couple really kind of key features within the M8500 product itself. And one of the kind of interesting things that you'll find in field-oriented control as an algorithm is there's a lot of trigonometric math because of the Park transformations. The Park and inverse Park transformation both involve trigonometric math, which can actually end up being a pretty big bottleneck in that field-oriented control loop if you're just using a standard software-based implementation. And so one of the innovations we bring on top of the standard RISC-V offering is actually bringing in trigonometric math acceleration within the CPU itself, all within the RISC-V standard. And so that's one of the examples within the use case itself, where you'll see these kind of, in addition to the RISC-V general purpose goodness, that MIPS is really doubling down on application focus across sense, think, act, and communicate. And so that's one example of that.
Okay, just quickly on that motor thing then. Obviously, as you say, you want to run motors at higher frequencies, you want them to be more efficient, you want them to be more compact.
Absolutely.
In some, so clearly anything you can do to avoid those bottlenecks that you mentioned that FOC would have,
That's
make
right.
that sort of system work a lot quicker and respond to any changes a lot quicker. And then also you mentioned that, things like robotic sort of grip and stuff like that, everyone's talking about that a lot more now. Well, that, or robotic surgery, for instance, things like where you've got to have very rapid sort of responsiveness, because if a robot's trying to pick up a delicate piece of, porcelain or something like that,
Right.
if it touches anything like sort of, too slow to react to what it's handling, it's going to break it or whatever it's going to do. And likewise, in a surgery point of view, it's got to be able to respond to
Extremely
haptic
precise.
feedback from the tissues and so forth when it's cutting or so clearly that those sort of things are really massively important. And as you were saying, standard FOC sort of arrangements using a motor controller would just not be able to respond quick enough to do that. Okay.
That's right. That's right. And maybe even just to give like in addition to, very precise control on the robotics side, with things like humanoid robots interacting with humans, that's another very key use case. But even like more tangibly in, smaller, lighter motors with electric vehicles, right? It's all about increasing driving range, that being one of the primary barriers to adoption of electric vehicles today. And one of the key portions of that is the weight of the motor. So definitely one of the key areas where system engineers are focusing is reducing weight, right?
Okay.
Reducing size and weight.
That's cool. And then you mentioned digital power conversion being another one, so maybe you could just give us a little bit of detail on that.
Yeah. So as our world becomes more electrified, there is power conversions everywhere. So when I talk about digital power conversion, I'm talking about anywhere there's a conversion of AC to AC, AC to DC, DC to DC, or DC to AC. And again, maybe to use the electric vehicle example kind of as a very clear example in terms of charging, right? When I plug my my electric vehicle into the wall or into my level 2 charger at home, I'm converting, grid AC to my battery high voltage DC, and that's a power conversion stage. And anytime there's a power conversion stage, there is some amount of power lost in that conversion.
Sure. Yeah.
So some amount of energy lost. So the name of the game in power conversion is efficiency, one. But then two, these power electronics themselves are include magnetics and large passive components like inductors. And so now you're talking about a pretty heavy, large piece of equipment. So in something like an electric vehicle, but also in something like your laptop charger that you plug into the wall, it's really the same thing, just scaled down a lot lower power levels. But the properties or the careabouts are the same: efficiency, power density, which means size and weight. And so again, the main goal is to reduce the latency of that digital power loop. But I would say even more so than motor control, this becomes extremely important in digital power conversion. And that's because switching frequency, being able to unlock higher levels of switching frequency, really drives down the size of the passive components
Yeah.
in order to increase power density. And so, in terms of things like that, you're charging, plugging a charger into the wall today, you'll notice that a lot of those chargers have really shrunk in size in the last 5 years or so, but have very high power levels. And that's all driven by higher switching frequency and smaller power stages. And also driven by more advanced semiconductor power technologies like silicon carbide and gallium nitride. But in order to use those more advanced semiconductor technologies, you have to support higher levels of switching frequency, which means you have to reduce the real-time latency on the CPU itself.
That makes sense, because as you move to wide bandgap, and like you say, you want to go to higher switching frequencies to get the greater efficiencies, reduce the losses. So if you've got sort of, much more sort of granulated control loops that can deal with things so much quicker, then you're going to get the benefits of that. And obviously that makes sense for things like you said, like chargers, but also, sort of the sort of the powertrains of vehicles as well. I'm
That's
guessing
right.
as well, obviously, as you said, conversions are going, there's more and more conversions taking place. But one thing is the way that we're starting to get towards where it used to be, the grid was just sending out energy to houses and factories and God knows what else. But
Right.
basically now it's potentially, you've got things like vehicle to grid, you've got microgrids, you've got all this sort of stuff where
Absolutely.
it could be that things are moving back. So the better the control you've got on that, and the more rapid the response, the better the efficiency of all those different conversions would be. Yeah. Okay.
That's right. Yeah. I mean, really, the amount of power conversion, whether it's in the vehicle, in the factory, in the grid, or even in renewables like solar inverters and the like, has really exploded in the last decade or so. And again, absolutely correct. As you make that control loop more efficient, you're also making that power conversion stage more efficient and losing less energy with every one of those conversions.
Okay. So those are a couple of examples there, and obviously then the third one was
Battery management.
battery management. Sorry.
Yep.
So yeah, when it comes to battery management, what would be the sort of
Yeah. So,
details of
so
that?
battery management is a little bit different compared to motor control and digital power conversion because the timing is not as critical, but the number of batteries or the number of cells being monitored
Yeah.
that has really increased.
Yeah.
So you're not as real time constrained as you are in motor control and battery management, but now you're becoming a little bit more data constrained where I'm getting a bunch of cell voltage and current data from my large battery pack. And I'm running algorithms like state of charge and state of health, but also some more advanced models like actually physically modeling the battery in models like P2D, which stands for partial 2D modeling. And these are really data intensive, more number crunching algorithms, so more compute, but spread over a longer time period. And that's really intersecting some trends around batteries growing in use, growing in size. So obviously electric vehicles is a very obvious example of that, but take your home, right? If I have a solar installation on my home today, and the sun goes down, I can't use my solar energy. And so having a place to store all that energy in a battery at my home has become, a much more common
Yeah.
use case. And so then I need some sort of monitoring equipment in order to make sure that that battery is operating correctly, but also operating safely, since that's a pretty large amount of stored potential energy that I have in my house.
And obviously, the pressures from the battery manufacturer's point of view, whether that's for vehicles, whether that's for ESS installations, like you just mentioned, is they want to fit
Right.
as much cell, sort of the cell density wants to be so fitting as much in as possible. So having that data allows them to work out, well, how far can they push those boundaries of what you can fit into a given space. And if you've got more data, then you can sort of it allows you to to actually do more with that and sort of push
Right.
the envelope further than you would otherwise. Okay, so
Right.
okay, so those are really three very good use cases there. That sort of all of them slightly different nuances, like you say, behind them, and some are more about latency, some are more about the sort of data in a more in a volume way. But all of those are sort of so. One of the things I know about, like, sort of, maybe it's a good point to talk about what you do as a company. Is MIPS have spent a long time doing multi-threading technology, and have sort of that sort of, I guess, must bring a great benefit for some of the use cases you've just talked about there.
Yeah, that's right. So I talked a little bit about motor control and the trig acceleration that we're bringing to the compute portion of the control loop. But when I talk about real time control in terms of reducing read and write, interrupt, and compute, compute latency is actually only one portion of that overall end to end real time control loop.
Yeah.
And so with real time multi threading, we're really solving the interrupt portion of the control loop. And so maybe I'll take a step back real quick on the multi-threading side in general within MIPS.
Yeah.
Multi-threading is a kind of core technology within MIPS, has been around for a long time, going back to the MIPS ISA as well. And it
Yeah.
is fully supported by the RISC-V ISA through this concept of hardware threads or hearts. And so we've really carried that forward into all of our RISC-V designs as well. And so you might not instantly think about multi-threading on the microcontroller side. It sounds like a high-level, high-performance technology, but we've really brought those same concepts down into the microcontroller space. But now, and this is why we're branding it as real-time multi-threading, but now we're solving a different type of problem. We're not solving as in simultaneous multi-threading that you would find in like the i8500 or P87 cores. We're not solving trying to cram more threads into the CPU for efficiency arguments. Now we are truly just trying to save clock cycles on context switch boundaries. And that's why this helps so much with interrupt latency. So with real-time multi-threading, we have multiple copies of our hardware context in the CPU itself. And then with multi-threading, you can, on a clock by or cycle by cycle basis, you can actually switch between the threads without any latency penalty that you would normally incur, for example, with servicing a high priority interrupt. And so, in a very simple case, imagine you have a background thread and my high priority control loop.
Yeah.
You would normally be servicing an interrupt when that high priority control loop interrupt comes, needing to vector to the correct interrupt service routine. And then once you get to the interrupt service routine, the first thing you're going to be doing is pushing all the current context to the stack using a bunch of push instructions. And that actually ends up being a significant amount of cycles, especially in these very latency critical real time control loops. And
Yeah.
so by having all the hardware directly in context, like the context in hardware itself, by duplicating things like register files being the best example of it, we can actually switch instantly to the other register file and let the high priority thread go without any interrupt latency incurred. And maybe my last point on that is just to make sure to differentiate from simultaneous multi-threading to real-time multi-threading. You're actually only allowing one execution thread into the pipe at a given time. Whereas in simultaneous multi-threading, multiple threads are allowed into the pipeline, into the CPU pipeline at a given time. So that's the real-time nature we're bringing to this. It makes it a real-time deterministic way of doing multi-threading for the purpose of reducing interrupt latency and context switch penalties.
Okay, so that's what differentiates it then, basically, is by making it real time rather than simultaneous. And so you're just avoiding some of those log jams, potential log jams that you just outlined there, making sure that it does stay deterministic in its operation, and you're
That's
not
right.
sort of, yeah, okay. So
That's right.
clearly, in a lot of the applications we've already discussed, that's going to be not just beneficial, but pretty much a mandatory sort of need.
Yeah, I mean, in all these real-time control loops, right? It's the
Yeah.
read write, it's the interrupt, and it's the compute. It's not any one of those things. It's actually all of them together that you need to have solutions for, and that's where like with M8500 specifically, right, where we have technology for the compute portion, which is the pipeline itself, but also the trigonometric math acceleration in the case of motor control. We have technologies for interrupt handling, in this case with real-time multi-threading. And stay tuned this year. We'll talk a lot more as we go through the year on the read and write side as well, that we actually have some specific technologies that we'll be announcing on the M8500 side for solving read and write latency as well. So really thinking about the problem end to end, not just one portion.
And I guess that's the thing, isn't it? Is you've identified these four different areas, and you've got to have solutions for all of them. As we said, they've all got to sort of integrate well together.
That's right.
But, you have to cover all the bases rather than just one part of it. Okay, so that's important from a MIPS point of view. Is you've got the portfolio to cover the sense, the think, the act, and the communicate sides of it. And okay,
That's right.
so that's cool. Then you mentioned the M8500s. So obviously that cause more dedicated, should we say, to the sort of ACT use cases we just discussed. So maybe you could just give us a bit more detail on that.
So M8500 is a 32-bit architecture microcontroller class CPU. It's a relatively high performance CPU targeting applications like we already talked about, like motor control, digital power conversion, and battery management, but also very well suited for some more general purpose tasks like communications, functional safety, for things like zonal architectures in cars,
Okay.
as
Yeah.
well as communication nodes within the factory themselves. And it does have all of the general purpose features you'd expect from a real-time microcontroller, like functional safety support, like cache support, like tightly coupled memory for low latency determinism, but also brings these more application focused features for solving real-time control problems like trigonometric math, like real-time multi-threading, in addition to all the things you'd expect from a 32-bit microcontroller CPU.
Okay. And like you say, that's the sort of MCU sort of side of this, and obviously the think one's a higher level. Sort
That's
of
right.
more. So maybe just to wrap up, maybe we could just sort of discuss some of the potential use cases that you envisage moving forward. You've mentioned some of the ones already that are relevant today, but what do you think are the possibilities for 5 or 10 years' time?
Yeah, so we talked a lot about real-time control on the ACT side, but I think as you move forward, you'll see a lot more intelligence coming to the edge. And so kind of battery management is probably a good example of that, of has how it's been more data driven. I think you're going to see a lot more data driven applications at the edge moving forward. So thinking about things like predictive maintenance or arc
Yeah,
detection at the edge
sure.
are kind of already there today, but will become even more pervasive on factory floors and in robotics, bringing that intelligence to the real-time control loop itself. And I think also, MIPS as a company is really looking heavily at the humanoid applications. I think that's probably a very key use case for sense, think, act, communicate. It's a very good example today, and it's not here today, but
Mm.
that's where we think the market is going 5, 10, 15, 20 years from now. And that for sure will bring, yes, real-time control, but a lot more intelligence and data compute needs at the edge for actually making some of that decision making local to the motor itself.
Okay, but as you say, predictive maintenance and condition monitoring and stuff like that, more use of robotics, and I guess the thing is that the more capability we've got to make things smarter at the edge, the potential use cases could open up, and I guess it's hard for us even to imagine where it could go in a decade from now, because those it's going to be an enabler to come up with more imaginative ways of using it, I guess. Yeah.
Yeah, and that really becomes the name of the game, is bringing more intelligence into these even small level microcontrollers, and really letting our customers, dream what they can do with all that compute power.
Okay, that's great. But like you say, it's certainly it's going to be a very interesting next few years, seeing where it's going to potentially go from here. So
Yeah, it's definitely an interesting time to be in the CPU industry, and I'm very excited about where it's going in the next 5 or 10 years. It's going to be a fun ride.
great stuff. Well, look, it's been a pleasure speaking to you again, Sean. Thank you very much. Really interesting, and hopefully I'll get to catch up with you later on in the year.
Yep, Mike, appreciate it as always. Appreciate the time, and yeah, look forward to chatting again.
Great.